In this video, we're going to talk about some properties of relations. Now recall that functions had a couple of properties. A function could be one-to-one, it could be onto, or it could be a one-to-one correspondence. These are sort of possible options or possible properties that a function could have. So now we're going to look at possible properties that a relation could have, but not all relations are going to have these properties. So relations can be either reflexive, symmetric, or transitive. Or they could be all three. These are not exclusive ors. So reflexive, what does this mean? It says a relation R over set A is reflexive if and only if for all elements in our domain, that element is related to itself. Okay, we say a relationship is symmetric if and only if for all x and y in A, if x is related to y, then y is related to x. Right? So the relationship goes back and forth. And transitivity, we say for all x, y, and z in A, if x is related to y and y is related to z, then x is related to z. In other words, the relationship sort of follows through or passes through the variables. And we'll see an example of this. So notice these are all universal statements. Right? So this isn't something that might happen here or there. This is a set is only reflexive if for every element in the set, that element is related to itself. And similarly, a relation is only symmetric if for every element x that's related to y, then y is also related to x, and so on. This is also universal. So let's see an example of this, because it can be a little difficult to really understand what's going on without a concrete example. So here's a relation. We saw this relation in a previous video. This is the divisibility by 3 relation with numbers 2, 3, 4, and 6, 7, and 9. And so we want to know, is this relation reflexive? Well, remember the definition of reflexive, which is for all x in our set, x is related to x. So for each element here, is it related to itself? Yes. Right? This, and the way we would describe this or demonstrate this is we could say that each element has an arrow to itself. Right? So this is a reflexive relationship. So now, is it symmetric? Well, let's write down the definition of symmetric. For all x and y in our set A, if x is related to y, then y is related to x. So is this relation symmetric? Yes, because whenever we have, for example, when 9 is related to 3, 3 is also related to 9. And when 4 is related to 7, 7 is also related to 4. Now you might wonder about 2. But in fact, if 2 is related to 2, then 2 is related to 2. It works. right? This is an if-then statement. So this only is true if x is related to y. So for example, it doesn't matter that we don't have a relationship from 2 to 3 because we didn't have a relationship from 3 to 2. So that's okay. So in fact, this is symmetric. Yes. And the justification is every time there is an arrow from one point to another, there's an arrow back. Okay. Transitivity is the one that I think students get caught up with the most. But in fact, and again, let's write out the definition. For all x, y, and z in A, if x is related to y and y is related to z, then x is related to z. So, and again, this is a conditional statement. It's a universal conditional statement. We're only concerned if these two criteria are met. So are those two criteria met? Yes. So if we call this 9, we call this x, y, and z, then if we have an arrow from x to y and an arrow from y to z, then we also have an arrow from x to z. See that? And in fact, this is the case everywhere in the graph. And even if you isolate like this 2 variable, well, if that's x, y, and z, then 2 is related to 2, and 2 is related to 2, so 2 is related to 2. So any of these chains, it's going to work. But this really, an easier way to think about it is that this only comes into effect when we look at these sets of 3, right? So in fact, this is a transitive relation. And the justification is for every 3 points, if there's an arrow from the first to the second, and from second to third, there is also an arrow from the first to the third. Okay. So now let's look at this chart and notice this is the same as on the previous page, except the previous page, this arrow from 6 to 3 also existed, and we have gotten rid of that. So now that arrow from 6 to 3 is no longer there. Okay, so is this reflexive? Does every element relate to itself? Yes. Every element relates to itself, right? There's still a loop here. For each element, there's still a self loop for every single one. Removing that one arrow from 6 to 3 did not change that. Okay, is this relationship symmetric? Think about it for a minute. No, it's not. And the reason is because 3 is related to 6, but 6 is not related to 3. Okay, and so that violates our rule of symmetry. And then similarly, is this transitive? No. And again, to disprove, to say that this isn't symmetric, I need a counterexample. So here's a counterexample. To give a counterexample for lack of transitivity, I can say that 6 is related to 9. Right, that's this arrow. And 9 is related to 3. That's this arrow. But 6 is not related to 3. Right? And so that violates transitivity.